Hi guys, what's up? This is just the first part of the series of lecture videos we're going to have for digital communication systems. And lecture 4 will focus on the discussion of digital binary baseband transmission. So all throughout this first part of this lecture video, we're going to ask ourselves what is the best way to demodulate. Actually guys, bear with me because this is the first time I'm going to do this kind of lecture video. Actually, I was debating with myself if I'm going to continue this, but since I'm very much inspired by BuzzFeed and Solve, I told myself, why not? So let's get right into it. This is a digital communication system block diagram. So you have already seen this block diagram before, so I have presented this one during our lecture 1 for digital communication systems. So this block diagram is actually the same thing as the communication systems with that in the analog. So we have the transmitter, we have the channel, and the receiver. So you have to recall that the transmitter is composed of the source encoder, the channel encoder, and modulator. So again, our target for source encoding is for us to integrate a data compression to our signals. As for the channel encoding, we're going to introduce some form of redundancy so as to counter the effects of noise. And for modulator, we're just translating or representing our signals into a usable form. Let's say, for example, in voltages and in currents. Now, in this lecture, we're going to focus on the effects of channel and how we're going to demodulate our signals. So we're going to focus that as we go along this lecture video. There is another way into which digital data comes into practice. The data may represent the output of a source of information that is inherently discrete, just like in the case of an output of a digital computer. Baseband transmission of data tells us that we're going to transmit our data as it is, without using any form of modulation technique or a carrier. Digital data have a broad spectrum with a significant low frequency content. This is how baseband transmission looks like in frequency domain. And this is for a bandpass transmission. So what is the difference between baseband transmission and bandpass transmission? So when we say baseband transmission, it is simply the transmission of our signals as it is without any form of modulation technique. So based on the diagram or graphical representation that you have seen previously, it resembles that of a low pass channel. However, if we want to modulate our signals first and then transfer that over the channel, then we have a band pass modulation. So as you can see there is actually a translation from a low frequency going to a much higher frequency for the cutoff frequency. Now we're not going to focus on digital bandpass transmission in this module, so that is to be discussed on the succeeding module that we're going to have. So in this case, we're just going to consider baseband transmission, or we are going to consider transmission of signals without any form of modulation. Therefore, in baseband transmission of digital data, a low-pass channel with a bandwidth large enough to accommodate the essential frequency content of the data stream is required. However, we have to remember that a channel always introduces distortion. And this distortion can be an additive or non-additive distortion. Hence, our channel can be noisy or band-limited. As a result, error may arise as a consequence of noise and or spectral modification of the signal. This is the effect of noise to our signal, whereas this is the effect of the dispersive property of the channel. We already know that a channel introduces a common property, and that is distortion, whether it is additive or non-additive. Now, for the additive effect of channel to our signal, so we have their noise. So there will just be a linear addition of noise to our given signal, whereas for non-linear, non-additive distortion, we have spectral modification. So one effect of spectral modification is intersymbol interference. Now, intersymbol interference affects our signal in a way that adjacent pulses are affected, thereby causing some error to our given signal. A pulse transmitted over a channel that is corrupted by noise can be modeled using an additive white Gaussian noise or AWGN channel model. Also, a channel modifies the spectrum of the signal as it has a dispersive property, meaning the frequency response of the channel deviates from its original response. The result of data transmission over such channel is that each received pulse is affected somewhat by adjacent pulses, thereby causing what we call intersymbol interference or ISI. We have here our transmitter, and our transmitter is composed of the source encoder, channel encoder, and modulator. The output of this transmitter is a series of ones and zeros. Let us name this series of ones and zeros as SM of T. This SM of T is to be transmitted using an AWGN channel, meaning to say there will be a linear addition of noise together with the signal. At the receiving part, we are going to do two processes. We have demodulation and detection. After detection, we're going to have a value which represents Sn hat, and this Sn hat is simply the approximation of our signal. Our target is that this Sn of hat should be the same thing as Sm of T. This is a closer look at our digital communication system. Recall that the role of the receiver is to reconstruct the received signal into a recognizable form of the original message. And it does this by doing two processes. The first process is demodulation and the second one is detection. Demodulation is the projection of the signal, basically to recognize the shape of the signal. Detection, on the other hand, involves deciding what the signal really is. Let's say, for example, we have a pulse signal represented by S of T. This pulse signal is to be transmitted using an AWGN channel. Therefore, this AWGN channel will introduce white noise. Let us represent white noise as N of T. Our received signal is simply the linear addition of our pulse signal S of T together with our white noise represented by N of T. We're going to use R of T as our filter input. Take note that our filter will be a linear time invariant filter. Again, when we say linear time invariant filter, this type of filter has an impulse response that does not change over time. Let us represent the impulse response of this LTI filter as H of T. The output of the LTI filter is Y of T. We all know that this Y of T is simply the convolution of R of T together with H of T. What we're going to do next is we're going to sample Y of T. We're going to sample Y of T at time is equal to capital T. This capital T represents the symbol interval. After that, we're going to decide what the signal really is. Is this logic 1 or logic 0? This is an example of a linear receiver. Consider a receiver model involving a linear time invariant filter of impulse response H of T. Our target is to determine what this linear filter should be in order to recognize what has been sent. If a signal S of T is corrupted with AWGN, the filter impulse response matched to the given signal will maximize the output signal to noise ratio or SNR. Maximizing the signal-to-noise ratio is very important, especially if we want to make our decision reliable. Consider again our received signal R of T. We're going to use this as our filter input to our filter which has an impulse response H of T in a time domain and H of F in a frequency domain. Our output is Y of T, and this Y of T is simply the convolution between R of T and H of T. We're going to sample Y of T at time is equal to T, or T here, the capital T, represents our symbol interval. Next, we're going to determine what this Y of T is. Y of capital T. Again, recall that R of T is our received signal, the sum of our signal with white noise. Next, we also have Y of T. Y of T is simply the filter output or the convolution between R of T and H of T. Note that T is from 0 to capital T, or this is the interval into which we're going to make a decision. So Y of T, we can represent that as the convolutional integral of R of tau multiplied to H of T minus tau d tau. Recall that the process involved in convolution are the following. So we have to fold the signal. Then after that, we're going to shift the signal, and then we're going to multiply and then take the sum. So R of tau can be represented as S of tau plus N of tau. Next, we can separate this term. So we can separate this term into this term. So S of tau multiplied to H of t minus tau d tau plus N of tau multiplied to H of t minus tau d tau. So as you can see here, if we know our signal, so we all know that our signal can be a symbol 1 or a symbol 0. So given a signal and then an impulse response, then you can determine a specific value for this given term. However, for this one, since we have noise, we all know that noise is random, then this one is a random signal or a random signal as well. So this one is deterministic, whereas for this term, this one is random. So let us represent this deterministic signal as y of s and this random signal as y of n. So if we're going to compute for the signal to noise ratio at our output, so again when we say signal to noise ratio, it's simply the ratio of our signal, the power of the signal, with the power of noise. Now if we are going to determine the signal to noise ratio here, then it follows that we need to determine the power of the signal and then the power of the noise. Since this one is simply deterministic, so we're just going to take the square of this given term, and then as for the power of the noise, what we're going to do is we're going to take the expectation of this given term. So this will now represent our signal to noise ratio at the output. So ys of t square, which will represent the power of the signal, is simply the square of s of tau multiplied to h of t minus tau. So this will now represent the average power of the signal. Whereas for the power of the noise, so what we're going to do, since this given signal is random, so we're going to take the expectation of the signal square. Now, expectation of the signal square represents the second moment, or it also represents the average power of the noise. So the average power of the noise is simply the square of this given term, the square of n tau multiplied to h of t minus tau. So let us just leave this given term first, and let us focus on this second moment. How are we going to determine this second moment? So the second moment, so we can represent or rewrite the second moment as the expectation of n of tau multiplied to h of t minus tau square. So if we're going to take, if we're going to distribute this power here, so we can rewrite it as n of tau 1 multiplied to h t minus tau 1 d tau 1 multiplied to n of tau 2 to the integral of n of tau 2 times h of t minus tau 2 d tau 2. So since expectation is just a linear operator, so we can rewrite this given term into the following. So we're going to have the double integral from tau 1 is equal to 0 up to capital T. So take note somewhere along the derivation. So we have substituted the small letter t here into capital T, because we all know that we have to make the decision from our given interval from 0 up to capital T, or the symbol interval. So we will now have a double integral from tau 1 is equal to 0 up to capital T, from tau 2 is equal to 0 up to capital T, and then we're just going to take the expectation of these two terms. So we're going to take the expectation of n of tau 1 multiplied to n of tau 2. So since our impulses are deterministic, so we're not going to include them inside this expectation operator here. So we're going to leave this outside. So h of t minus tau 1 multiplied to h of t minus tau 2 d tau 1 d tau 2. So as you can remember, if you are going to determine the changes that is happening within your signal, or you're going to correlate your signal with itself, then we're going to have here an autocorrelation. Okay, so this expectation of n of tau 1, n of tau 2 simply represents the autocorrelation of your given noise. So we have to recall, what do we know about noise? So when we say noise in this given case, so noise is white and it is Gaussian distributed, or it is normally distributed. So noise has a constant power spectral density equivalent to n naught over 2. So I hope you can recall that the power spectral density of a white and Gaussian distributed noise is n naught over 2, and its autocorrelation function is simply equal to delta. So rewriting this given term here, so we can represent the autocorrelation as simply the power spectral density n naught over 2, and then we have the delta. So we can represent this one, since we all know that autocorrelation is simply you are correlating the signal with it itself. Then you can represent the time difference of your given noise as a delta of tau 1 minus tau 2. Then just retain the other terms here. So we all know that if this is the case, so we all know that for the autocorrelation function of noise, it has a value at tau is equal to 0, and the value of noise at tau is equal to 0 is n naught over 2 delta of tau. So recall that the autocorrelation function is simply 0, okay? So 0 except when tau is equal to 0. So you will only have a value when tau is equal to 0. Meaning to say, the whole term will make sense if we're going to make tau 1 equivalent to tau 2. Okay? So we're going to make tau 1 equivalent to tau 2. So when tau 1 is equal to tau 2, we all know that this will be equivalent to 0. So we can rewrite this given term as n naught over 2, delta of 0, h of t minus tau, h of t minus tau. So take note, we're going to just represent tau 1 and tau 2 as just tau. Then d tau. Then we can rewrite, since n naught over 2, so we are actually evaluating in terms of tau, therefore we can factor out, or we can remove inside the integral n naught over 2, and then we all know that the integral of a delta is simply equivalent to 1. So we're going to have here n naught over 2, integral from tau is equal to 0 to t, h squared of t minus tau d tau. So this is now the equivalent of the average power of noise in our given system. So let us represent this one as equation 2. So integrating the two equations that we have determined a while ago, so we can represent the signal to noise ratio in this way. So the signal to noise ratio is simply 2 over n naught, and then our numerator, which will represent the average power of the signal, is simply the integral from 0 to tau, 0 to t, s of tau, h of t minus tau. Take note, this whole term is raised to 2, okay, since we are determining the average power of the signal, divided by the integral from 0 to t, h squared t minus tau d tau. So this is what we have derived a while ago. So this represents the average power of noise. So take the reciprocal of this one, since this one is on the denominator. So this will be 2 over n naught. So this represents the signal to noise ratio at the output. However, we're going to do some manipulation on this given equation so that we will arrive into somewhat more manageable form of equation for us to determine the signal to noise ratio. Well, they say that the most ambitious crossover ever in the history is Marvel's Infinity War. But then again, I'm going to present you this. Consider a set of continuous functions on an interval a and b. This set, along with the addition and multiplication with scalar values, forms a vector space. Right? As you can see there, vector analysis doesn't leave you. Actually, all the other topics or all the other principles that you have studied previously, so they will be applied in digital communication. So it is actually an integration of several different topics. Signals can also be viewed in vector domain or in a signal space. So let's say, for example, we have here signals in time domain. So we all know that we can represent signals in time domain and also in the frequency domain. However, there is also another way for us to represent our signal, and that is in a signal space. So let's say we have here S1, and this S1 here can be represented in a time domain or a single dot in a signal space or vector space. And then another one here is S2. Again, S2 can also be represented in time domain or in a signal space. Now, if you're going to represent signals in a vector domain or in a signal space, then we can also perform what we call dot product on these two signals or in these two vectors. Now, if we are going to perform a dot product in these two vectors, they can be represented in this given notation. Now, this notation, wherein they are enclosed in less than or greater than sign. So this notation represents dot product between your signal S1 of t and your signal S2 of t. Now, if you're going to take the dot product between these two signals, it is represented as the integral from your given interval a and b, then the product of S1 of t, S2 of t, dt. Now, I'm not going to elaborate for now we're not going to elaborate for now how we're going to translate from the time domain to a signal space or vector domain, because that is not the scope of this lecture. Instead, that is going to be tackled on our next lecture. Now, take note that the given notation represents the dot product between two signals, or again, when we say dot product, it is simply the projection of one vector to another, or in this case, from one signal to another. Now, there is what we call the Cauchy-Schwarz inequality. Now, recall that if we are going to take the dot product between two vectors, so let's say I have two vectors g1 and g2, so for me to determine the dot product or the projection of g1 to g2, I'm just going to take the product of their magnitude multiplied to the cosine of the angle between them. Now, let's say, for example, I want to determine the magnitude square of the dot product between these two vectors. Now, if I'm going to take the magnitude square of the dot product between these two vectors, it can be represented as the magnitude square of g1 multiplied to the magnitude square of g2 multiplied to the cosine square of the angle between the two. Now, using the Cauchy-Schwarz inequality, we can say that this given term, the magnitude square of the dot product between two vectors, will always be less than or equal to the product of the magnitude square of g1 together with the magnitude square of g2. Now, this is because the cosine of an angle is always smaller than 1, unless the vectors are in parallel with each other. Now, if the vectors are in parallel with each other, then you're going to have the maximum value of the cosine of a given angle. Now, this given inequality here is represented as, or is being expressed by what we call the Cauchy-Schwarz inequality. Now, this is just one form of the Cauchy-Schwarz inequality. There are also other forms of this one, but this notation is somewhat easier to understand, so I just represented it this way. Now, we can now conclude that using the Cauchy-Schwarz inequality, if we are going to take the magnitude square of the dot product between two vectors, it is always less than or equal to the magnitude square of g1 multiplied to the magnitude square of g2. Now, this holds true when the two components are in parallel, or this will be maximized if the two components are in parallel. Now, how can we say that the two components are in parallel? We can say that the two components are in parallel if g1 is simply equivalent to g2, and then you're going to use some k or just some arbitrary constant here or gain. Or you can also say that g2 is equal to g1 using, again, this some arbitrary or constant value k. So again, k is some arbitrary constant or gain. So where we're going to use this Cauchy-Schwarz inequality? So we're going to apply the idea of the Cauchy-Schwarz inequality in our numerator. So what we're going to do is we're going to represent S of tau as our G1 and H of t minus tau as our G2. So recall that this is the signal to noise ratio that we have derived previously, and again this form is not that manageable, so we're going to do some form of manipulation. So as you can see here, this term somewhat resembles this given term. So this represents the dot product, or the dot product and then the magnitude square of this given two signals. So what we're going to do using the Cauchy-Schwarz inequality, now this given term here will always be less than or equal to this given term. Now why is that so? Because we are going to expand this term. So as you can see here, since these two are somewhat similar, then we can rewrite this term into this term. So what we're going to have is the integral from 0 to t s square of tau d tau, because we said here that the magnitude square of the dot product of G1 and G2 will always be less than or equal to G1, the magnitude square of G1 multiplied to the magnitude square of G2. So therefore, magnitude square of G1 is simply S square tau d tau, take its integral from 0 to t, and then magnitude square of G2 is simply the integral of 0 to t of h squared t minus tau d tau. So as you can see here, based on our given expansion, there are terms that are now equivalent to each other. So the denominator and then some term here in our numerator are now equivalent. So we can just rewrite this one in this way. Therefore, the signal to noise ratio, take note, will now be always less than or equal to 2 over n naught, integral from 0 to t. So this is now the remaining term from our given numerator. So s square of tau d tau. Now, there is what we call the Parseval's relation or Rayleigh's energy theorem. Now, what does this theorem mean? That if you are going to take the magnitude square of a given signal and then integrate that from negative infinity to positive infinity, whether it is in time domain or in frequency domain, then you are going to obtain the energy of the given signal. Now, since this form resembles the some term in the signal to noise ratio that we have previously obtained, then we can rewrite the signal to noise ratio as simply twice the energy of the signal divided by n naught. So meaning to say, if we're going to interpret this given term here, that the signal to noise ratio at the output will always be less than or equal to twice the energy of the signal divided by n naught. Now, when is this given inequality hold true? Now recall that the maximum value, or in this given case, that the maximum value of the signal to noise ratio at the output is simply twice the energy of the signal divided by n naught. Now this maximum value will be satisfied if the following conditions are also satisfied. That whatever G1 that you use will be equivalent to kG2, or your G2 is equivalent to kG1. Again, K here is some arbitrary constant or gain. But we all know that we have represented G1 as S of tau and our G2 as H of t minus tau. Therefore, we can derive the following conditions in order to satisfy the maximum value of our signal to noise ratio. So we can say now that if we are going to maximize the signal to noise ratio, our signal should be equivalent to some arbitrary constant multiplied to the impulse response that is flipped or folded and shifted by t. Or we can also say that the impulse response of your given linear time invariant filter should be equivalent to some k or arbitrary gain or constant multiplied to the signal that is flipped or folded and shifted. Now this given impulse response is what we call the match filter. So meaning to say, what we're going to use here in order to maximize our signal to noise ratio and for us to have the best decision at the receiving side, we're going to use a match filter. Again, if we're going to interpret what this match filter do, so what it does is that It is just equivalent to your given signal that is folded and shifted by t. Now, in that way, we can now maximize our signal-to-noise ratio. Or we can say that our signal-to-noise ratio will be equivalent to twice the energy of your signal divided by n naught. So in this case, we are now assured the signal-to-noise ratio at the output is maximized. So we have seen that the best way to demodulate our signals is using a match filter. Again, for the match filter impulse response, it is simply equivalent to the signal that is folded and shifted. Now, why do we need to use a match filter? Because we want to maximize our signal-to-noise ratio. And why do we need to maximize our signal-to-noise ratio? We need to maximize our signal-to-noise ratio because we want to minimize the probability of error. So in order to maximize the signal-to-noise ratio, the impulse response of the filter should be equal to the signal that is folded and shifted. This type of filter is called a match filter. To be able to detect the pulse at the receiver, the peak pulse signal-to-noise ratio, or PSNR, so we're just going to rename the SNR that we have previously used into a peak pulse signal-to-noise ratio, or PSNR. So it has to be maximized. So this is the configuration that you're going to follow if we are going to use a match filter. So as you can see here, we have here your received signal that is corrupted by noise. So we're going to use actually two match filters here. So a match filter that is matched to your symbol 1 or logic 1, and then another match filter that is matched for your symbol 0 or logic 0. So what you're going to do here, just take the sum, actually take the positive output of your match filter for symbol 1 here, and then subtract the match filter output for symbol 0. And then we're going to sample that at the time interval capital T, and then we're going to use some form of threshold which is used for comparison whenever we're going to do some decision making. So let's say if we exceeded the threshold, so we're going to decide that this is logic 1, or if we have less than the threshold, then we're going to consider this as logic 0. So we're going to discuss that later. So if a signal is corrupted with AWGN, the filter with impulse response matched to the signal maximizes this PSNR. It is clear that the maximum PSNR does not depend on the waveform of the signal, but the design of a match filter is dependent on the pulse shape, because if you can remember, the match filter is simply the signal itself that is folded and shifted. Therefore, we are dependent on the pulse shape of our given signal. What we're trying to do is to make a door tailored for the signal. The noise will also squeeze in, but in a fashion that the PSNR is maximized. Note that the match filter is not an ideal filter. It is actually frequency selective, but we're not trying to preserve the shape of the signal. What we're trying to do is we are trying to maximize PSNR to make the best decision later. So that's it for now for part 1 of this lecture video. So I hope you were able to understand what is the best way to demodulate our signals. And again, that is through a match filter. And for you to appreciate more how this match filter does its match filtering, so we're going to answer some sample problems on the next part of this lecture video. So I'll see you there.